All right, can you believe it? We are just about done all the AC motor theory. Not the controls, but at least the motors. We're on to our very last of the learning tasks for the motors, which is going to be oddball motors. Other types of single-phase motors over here. Once again, this is a single phase application that we are going to be looking at all throughout here. And the reason that, even though year 3 is mostly all 3-phase stuff, the reason that it's being done this way is just because we had to establish a lot of our other, base theory as to how a motor itself actually goes and operates. So the very first one that we are going to talk about is going to be the universal motor, which sounds fantastic. Because we like it when there is one thing that, takes care of absolutely everything. Universality is a really, really great thing. However, usually when something can do everything, it kind of does everything poorly. And we see that inside of this AC universal motor as well. It is very constructionally similar to a DC series motor, and it will operate on DC as well. The big difference is that these ones are going to go and have lots of laminations. Okay, because we have got AC, we have got all of our shred losses that are going to go and happen. And as soon as we've got all the shred losses, that means that we need to try and eliminate them. So we're going to go and put in all those laminations as necessary. Okay, so let's look at this connection, because the connection is going to go and tell us a bunch of stuff operationally. And we're going to go and take from this connection, we're going to go and create a drawing off of this. First thing that we're going to go and talk about is the fact that our armature is going to go and have windings. This is not a squirrel cage one. This is one that's going to go and have actual windings going from commutator section through some windings and then coming back to another commutator section. Okay, so we have to understand that there is an armature winding that is going to go and happen inside of here. And if I were to follow this along, I see that from line 1, I go into a brush and an armature. So I'm going to draw that up top over here. We're going to say line 1, we're going to go into a brush and then into an armature. Put that in like that. We come out of the armature and then we are going to go into a series winding. Okay, we're going to have our current that's going to be passing through here, passing through here, passing through here, passing through here. And then we see that it is going to go and come back from that series one, and it's going to go and pass over again a couple of times and pass over again a couple of times on its way out. So basically what we end up with over here is we are going to go and end up with a large series winding with all of our current coming into this motor and out of this motor through both the armature and through the series field winding. So what does this thing do when it's on AC? Well, I mean, right now we've dealt with the DC series motors before, and we haven't even talked about, trying to apply them to AC. We did go through something that was really cool, though, before in DC series motor, and you had no idea that you were setting in a little bit of a foundation for what we were going to cover here, but that was where we start to talk about reversing of a DC motor. And when we reverse a DC motor, we found out that we can go and reverse that DC motor by doing one of two things: either reverse the armature or reverse the fields, whichever one we'd prefer. The standard is to go and reverse the armature. We did find out that on my DC motor, that if I were to go and interchange the lines, if I had a positive negative here and I were to go and change those around and make them into a positive here and a negative down over here, that then my motor would still have thrust in the same direction. It's still going to go and rotate in the same direction, even though we had gone and interchanged the lines. If you think about it right now, it should be immediately apparent to you that us changing the lines is the exact same thing as what an AC supply does. AC supply goes positive, negative, positive, negative, negative, positive, negative, positive, positive, negative, etc. across there. So if changing the lines on a DC series motor does not change the rotation of the DC series motor, but makes it continue to rotate, why would it be any different over here when it's now automatic that's happening, right? That's really what we're looking at over here. Okay, construction, just a couple of last details we've got to talk about on them before we start looking at this operation. The big things that we have to talk about on these that are going to be different are just going to be the ways that we're trying to, once again, eliminate a lot of extra losses. We talked about the fact that our stator is going to go and be laminated, right? Different layers with varnish in between. So we still can go and use the ferromagnetic, the magnetic components of that, but we don't have all the losses from our eddy currents that we are going to have inside of them. The other thing that we are going to go and have is we are going to go and have the fewer turns that we are going to go and place off of these windings. In a DC machine, we will place more turns inside of here. But on an AC machine, we need to go and put in fewer turns because we are going to, and we'll just compensate for that by dumping more amps through it, because otherwise we end up with too high of a value of XL, right? XL is going to be based upon my L, and L is going to be based upon my number of turns, right? L is equal to N squared mu A over top of little l. If I have too many turns, I'm going to have too high of an L. XL is based on 2 pi FL. If I have too much L, I'm going to have too much XL. And if I've got too much XL combined with my resistance, I'm going to have too much impedance and not enough current. So we're just going to go and have fewer turns so that we can not lose everything to all of our XL. And we'll just dump more amps through these correspondingly. Rotor is also going to be laminated off of these. It is going to have actual windings. It's not going to be solid. It's going to have skewed slots, the same as a regular squirrel cage, just so we get smoother operation, etc. Now let's go and talk about the actual operation. Over here on the operation, what they're not showing us is they're not showing us the actual winding that is going through in the back. So I want just mentally you to make this connection. Okay, I'm just doing a dotted line over here showing that we have got a winding that is passing through from one side to the other there, kind of in the back, okay? And we're now just going to go and pass current through this thing in different directions. The first one that we are going to do is we're going to pass this current through in here. When I pass this current into this one here, this is a negative. This is a load, right? It's a motor. So we're going to go and pass current in. The current is going to go and disappear down and into here. And then the current goes through that dotted line, the red bar we see at the back, and then comes back out towards us here. And then it travels through, and it's going to go and travel down and around, down, 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 down. It's going to get up to here. It's then going to go and travel down and around, and it's going to go and travel down and around like that there once again. And eventually it goes and leaves this. What we have over here right now is we have got absolutely everything that we would need to go and establish direction of rotation. You can use your right-hand motor rule where you're going to go and keep your finger folded in, right? Your thumb folded in. You're going to look at your first finger in the direction of the field. You're going to go and look at your center finger in the direction of your thrust that you are going to go and have. And you would be able to go and determine that. Let's just deal with this bottom one right over here. It's the easiest one for you to go and move your finger around the proper directions. If I look at it, I see that I'm going to go and have a field going across like that. That's going to be my first finger. And I see I'm going to have a center finger coming towards. So I want to put your first finger facing vertical up in line with the green arrow. Fold your center finger out towards yourself there. As you go and do so, you should be able to go and establish a thrust. Make sure you are using your right hand rule for this one. When you do that, first finger in the direction of fields. First finger in the direction of fields, the wrong direction here. This is a south pole over here. My bad. The flux lines are going in the opposite direction. Wondering what was going on here with the arrowheads. It's going through like that, okay? That's our direction going through from north to south, so we're going to go with that one. Your first finger should be pointing down. Your center finger should be pointing towards yourself, and then your thumb should be then lined up with this arrow over here. We see that we're going to go and get that thrust in that direction. We could also go and do that thing off of our left-hand rule, and we'll just quickly do it off of the left-hand rule, which would be that I'm going to go and have circulating currents going around this one in that direction, left-hand rule for conductors, and I'm going to go and have them circulating in the opposite direction over here where it's going into that conductor, right? All we would need to do is just fire our line of flux from the north. It's going to get fired down here. It's going to get caught by that, torn around in that direction. It's going to go and continue down straight. And then over here, it's going to get torn around in that direction over there. And as a result of that, we see we have got a slingshot up top that's trying to kick this thing out in that direction. We see we've got a slingshot on the bottom trying to kick this thing out in that direction over there. We see we get this direction of rotation. Let's do the same thing on the other side over here. Now we're going to go and have our AC supplies. This is my AC supplies now changed its direction. So we've got a positive negative. Current comes in here, which means it's going to be traveling up like that, traveling up like that. And then it's going to go and travel in on this one. So it travels in, down, into there, and it goes through that red conductor in the back over there, and then comes out towards us over here. Once again, right-hand rule, stick your first finger in the direction of the field. I'll get it right this time, north to south, looks like that. Put your first finger in the direction of field. We're going to examine this bottom one, because the bottom one, I guarantee you, is easy to go and do with your right hand. First finger in the direction of field, center finger in the direction of current, facing in towards the page, and you should see that your thrust, your thumb, using your right hand, is going to be pushing us out that way. Thumb is going to go and kick us out that way. This one over here is going to kick us out this way. What we see is that because we have simultaneously reversed both the field and the armature at the same time, and we're not actually doing it, it's the AC supply that's doing it, we are able to go and maintain direction of rotation off of them. Fantastic. Because now we have got a motor that we could operate off of AC as well as DC. Now, we don't do that a lot. But we do, sometimes have a place where you could potentially go and utilize this. We're going to get less out of the fact that we can go and operate this thing off of AC or DC. We're going to get more out of the way that this thing acts when we go and operate it inside of AC. Because if I look at it, the simple drawing shows that I've got an armature with a series field. And when we looked at the DC machines, DC motors, you should remember that the torqueiest of all of my DC was going to be the series DC motor, right? Where the more current that we pass through, and that's what we have over here as well. So the more current, we'll go negative, positive, but the more current that I pass through the armature, the greater the field that I'm going to go and have around that armature. So it's going to go and make a bigger field around that armature. Well, at the same time, that current is also going through this, which is creating more lines of flux. So I'm going to have more lines of flux that are going to be created, and they have to go and get distorted. They have to go and get pushed out much further. And because they're getting pushed out so much further by the massive field around here, they're going to have a bigger slingshotting effect, right? It's just a bigger slingshot. So it's the same slingshot, but you're pulling it back further down, which means you're getting more velocity out of these things. That's where these things are going to go and shine, not off of the fact that we can interchange an AC and a DC supply, because we don't have a lot of supplies that have the same voltage characteristics, even just to begin with, 240 volts or 120 volts, etc. It's not very common to have those inside of a DC. This is also, the universal motor is only able to be operated on AC and DC. A DC series motor, I should clarify, could not be operated on AC, and it's really just due to the fact that our DC machines are not going to be laminated, so we're going to get huge eddy current losses. We are going to go and have more turns, so we're going to have more reactance, which means that we're going to go and get less current out of our motor. It's not going to be as strong. And we are going to go and get some really, really high circulating currents inside of our brushed out windings that we are going to go and have, which would mean that we just get a lot of damage off of our commutator. So a universal can be operated on AC or DC, but a DC cannot be operated on AC. Okay, let's take a look at this over here. This is a very, very important thing to us, where it's going to be a speed load graph that we are going to go and have that is also going to be lined up with another graph. I'm just going to go and overlay that graph over there for torque. Can't spell torque here right now, not sideways at least. Torque that we are going to go and have. And torque would be, we'll graph that one along this side over here compared to this bottom side here, which we're going to go and take a look at slip. Okay, what we would see off of this thing, if I were to graph torque versus slip, I would see that when I'm at 100% slip, that's going to be when this thing is at a standstill. I'm going to have a massive amount of torque, but then that torque is going to go and drop down as I get closer and closer to my full rated speed that I'm going to go and have. And so I get this torque curve over here that is going to go and be in opposition to my speed curve over here. I see that when I need very little torque, I'm going to have a wicked amount of speed that I'm going to have out of it. And when I need a lot of torque, I'm only going to go and have a tiny amount of speed that is going to go and come out of these ones. That makes them very, very useful for a couple of components. These components are going to be ones where we need to go and get some high amounts of speed, but sometimes we need to go and start with something that's going to be, relatively hard to go and push through. One of the best places that I can go and that you probably have used them before is inside of a blender. I want you to think about a blender that is going to be full of ice, right? You got your blender, you're going to go and make your post-workout smoothie or whatever it is, and you're going to go and have all this ice that's going to be down here in the bottom. You've started these things out, and you hear them bog down as that thing starts coming up there, and then all of a sudden it gets up to this wicked high speed once it pulverizes everything inside there. This is important to note that a blender has got a series motor. Not because you're going to service one, you're going to throw it out, you're going to get yourself a Vitamix or whatever at some point. It's more so because this, knowing that I've got a blender over here, helps me as an electrician to go and troubleshoot. Because I know that that blender incorporates a series type of motor, a universal motor. And most importantly, what I don't know about this is that that universal motor incorporates brushes. Now, I'm going to go put off a whole pile of arcs and sparks over here at the brushes, because that's what happens with any type of brush machines. There is always going to be some arcing and sparking. How does this affect your job? Well, let me introduce you to this wonderful little thing that we all know called the Afci, Arc Fault Circuit Interrupter Circuit Breaker. This is a circuit breaker that is monitoring the current, looking for telltale arcing. And when it sees arcing, then it's going to go and shut that thing off. It's designed to go and trip out because it knows that it's seeing the signature, and there's a specific type of signature to the current that is going to be tied to an arc. In this case, in my blender, blenders and AFCIs don't play well together, because that blender has got that little brushed motor, and in the very bottom of that, there's going to be little sparks coming out of that thing. Some real crap blenders, you can actually see the sparks spitting out of there. You can smell them coming off of it sometimes. The other place that we have got these series motors, where we once again have got, when it's at load, it's going to be slow, and then when it goes to no load, it's going to be high. It's going to be inside of a vacuum cleaner. Vacuum cleaners, if you stick your hand over top of the nozzle of the vacuum cleaner, you hear that thing go, whoo, because at that point, we're no longer pushing any air through it, which means that it's lost its load off it. That's why it's going to such a high speed over there. But as soon as you take your hand off, all of a sudden it's pulling stuff through. And that's, going to be back to its normal operation. It goes back down to this, full load type of speed that we have. Once again, my vacuums don't always play nice with my AFCIs. So if you've got a customer that is always, complaining, or says, these AFCI breakers, I know that I have to have them in here, but it keeps tripping out, tell them to buy a new blender, or tell them to buy a new vacuum. If they inherited their, old Hoover from their grandma, it's maybe time to get rid of that thing and get something that's got a better motor in it, so it's not going to be tripping out, because it's the motor inside of those. It's not a bad breaker. It's a good breaker. It's doing what it's supposed to do. It sees that there's an arc, and it shuts it off, because our breaker doesn't know that that arc is coming from one of these series types of motors. Anyways, this is just, for your information. There is that arc inside of there. Therefore, we are going to go and have to deal with it when it goes and causes problems on our systems. And since we are the ones that control the lightning, we put the AFCIs in, and our customers expect us to be able to tell them why stuff is tripping out. Series motors. Very common. The other place that, by the way, that does trip out AFCIs quite commonly as well is smoke detectors. If I've got ionization types of smoke detectors, older ones or something like that, those ones can sometimes go and cause it, because it's a free flowing amount of current, in the ionization, small decay of nuclear positive type of material, basically, and we're getting these ions that are pushing through there, and so it's going to be this current that kind of has weird characteristics that's similar to the arc type of look, which will sometimes trip them out as well. So if you get a weird circuit that kind of keeps going out on AFCI, check if your smokies are on it. If your smokies are on it, just replace it with new smokies. Should take care of that problem if they aren't plugging other stuff into it. Okay, let's talk about this thing, the shaded pole motor. Now, the shaded pole motor is going to be used a lot, and we don't actually usually see it looking like this over here. What we most commonly see is we're going to go and see a shaded pole motor that's only going to go and have two pole faces. Okay, I'm just going to erase these ones over here. And the most common place that we see these little two-faced beasties is going to be inside of my bathroom fans. And usually what they look like inside of my bathroom fans is going to be a relatively small type of, you'll see the same sort of face over here, but then it is going to go and have like a square section that comes off here. And the purpose of my stator inside of here is to go and complete the magnetic lines of force. So we are still using, even on those little ones that you have inside of a bathroom fan, etc., we are still going to be passing. It has an outside loop, so we can pass all of our magnetic lines of flux back through and then fire them through from one side to the other. But it's pretty rare to go and see them built with these 4 poles off of them. Some of your higher efficiency bathroom fans will use these 4-pole ones, but most of them are going to go be 2-pole ones. We're going to go and have a couple of different windings off of these. We're going to have some windings that are going to go and be outside energized. That's going to be these ones here, which are going to be our exciter windings that are going to go through, etc., all the way back out. And then we're going to have another one that's going to be called my shading winding. And what's really beautiful about the shading winding is it is just a copper bar. Okay, we're going to have laminated steel because we're working with AC. And then what happens is that around this one here, there's just going to be a short-circuited copper bar that goes around each one of these. Okay, let's draw a couple of these across here, etc. And these are copper conductors, which means that when we have got a magnetic field near them, Eg is equal to BLV. Flux length, or flux density, my length and my velocity is going to generate a value of voltage. So we can generate values of voltage in here. Because it's copper wrapped around steel, the current's going to want to flow through the copper. It's not going to want to try and go through that steel inside of there. And so we'll generate these values of voltage, which are then going to cause currents to go and circulate around those. And those currents are going to go and interact with other stuff. Now, this shading coil over here is also a bit of a damping coil. You sometimes hear them called damping coils when we're looking at contactors, but it's got the same purpose. You know, that brass bar that goes around, if you've ever pulled out a contactor, an AC contactor, that shading coil is going to be on there, and it just acts to go and act as an inductor. Let's talk about what does an inductor do. Well, an inductor opposes any change in current, right? It does not like to see current change. If current is at 0 amps, it likes it. Okay, it approves of 0 amps and it doesn't want to see that current going up. If the current tries to go up, it's going to go and fight it. Can't fight it forever, the current's still going to win, but it's going to try to fight it. If the current is high, if the current is at 10 amps, it likes that as well. And if the current were to try and drop away from the 10 amps, it's going to go and fight that as well. Basically, an inductor is just this pissy little bit of electrical that tries to fight any sort of changing current. It does not like it when the current is going to go and be changing. And the way that it fights it is through magnetic fields, right? It's going to go and induce, it's going to collapse lines of flux around itself to go and induce values of voltage, which it can then use to go and maintain current off of it. Okay, let's look at how that actually operates. What we are going to see is that going across each of these, we are going to go and have a north pole and a south pole, and it's going to be a moving north pole and south pole. By the way, before we do that, let's look at this one over here and just put current through in one direction. I don't care which direction. Let's say that the current is coming in here right now. If the current were coming in here right now, and it's going to go travel through, and then in here, here, like that right now. If you were to go and use your left-hand rule, you'd see that this one here is a north. And then you would go and see that this one here is a north. And then you'd see that this one here, because the current comes around, goes up in that direction. That one there is going to go and have its north here. And if I were to take a look at this current, that current is going to be traveling down in that direction. I'm tracing it around. I would see that this one here would be a north as well. So I'm going to go and see a south here, right? So we see a north-south, north-south, alternating, going around here. What we're going to have happen inside of here is we are going to go and have norths and souths, and we are always going to go and move strength of our field. Our field is going to go and rotate across this. That's why it's got this weird shape to it. We got this section over here, which is going to be called the unshaded portion. We're going to have the section that has got that copper bar around it. That's going to be called my shaded portion on each one of these. And so on each one of these, my north is going to start strongest there, move across here. Same with my south is going to start strongest there. And then on the next alternation, current would change, and then I would have a south that would start over here and then move across at the same time as I've got a north that would start over here and be moving across as well. So always moving across these. Let's take a look at current. Now we're going to go and examine current over here. This is a graph of my actual current that is going through here, not a graph of my voltage. And we have to refer back to this formula over here. E is equal to negative L delta I over top of delta T. Okay, this is going to be my formula for counter EMF when I'm looking at a coil. And that's all we're doing right now is we're just looking at this as if it were a standalone coil. So, does this thing have an L? Absolutely. There's going to go and be, we're only talking about the shading coil here, by the way. There's going to go and be some sort of an L because it is a coil of wire. It possesses inductance. I don't know what that value is, but it's going to stay the same. No matter where we are throughout all of these cycles over here, L will stay the same based upon its physical characteristics. What about time? Does time change? No, time doesn't change. So we're going to go and take a look at stuff that's just short little sections of time. We're going to always look at the same value of time for each one of these. But what we do see is we're going to go and have a rate of change that is going to go and happen. Over here, this is a steep rising current, which means that its change, the amount that is changing over top of time, is fairly large. Okay, so this is going to be a large value. The change in current over top of a change in time is going to be large right over here. If I compare that to this section over here, the change in magnitude of current over top of the same length of time is going to be much smaller. And then over here, I would have a large amount. Over here, I would have a large amount. Over here, I would have a small amount. Change the magnitude of difference over top of the change of time is going to be small. And then over here, I would go back to having a large amount again. So we're going to reference this one here, the counter EMF one, because the counter EMF is going to go and be what we'd have inside of a regular conductor, but counter EMF also corresponds to transformed values of voltage. Remember back from second year that your secondary voltage is always in line with your counter EMF. Okay, so looking at this now, let's go and do some analysis. The first thing we're going to look at is we're going to go and take a look at this over here, where we've got current traveling through here. Use your left-hand rule. You should see that you are going to go and have a north down there. Once we've established that north, then we're going to go and say, well, these lines of flux are going to be created. They're going to be traveling through here. Now, when those lines of flux go and encounter this over here, they're going to go and cut through that conductor. And when they go and cut through that conductor, we are going to go and generate some sort of, well, we have to go and have some sort of a current that is going to go and be induced. First of all, is my current rising right now? Absolutely. My current is rising right now. So my lines of flux around here are going to be becoming larger and larger and larger. I'm going to go and just draw this edge really, really large, okay? This over here corresponds to this edge over here. We're going to go and have these conductors that are coming around the outside. I'm going to take a cross-section of this one. I'm going to take a cross-section of this one. And then I'm going to go and use a different color. We'll use gray to go and take a cross-section of this holding coil over here. Okay, so this is just going to be that conductor as it's wrapping around the outside, that conductor as it's wrapping around the outside, and this over here is going to go and be that shading coil conductor. Oh, I think I said I was going to do that gray. Let's change that. That's the cross-section of that one. Okay, they do wrap all the way around each of these conductors, but I want to just take a look at these things as they are across here. Looking at these right now, so now that we know what we are looking at for these, we see that the current is coming across the face of this, right? It's coming across the face of this, which means it's going to be entering into there and going around to the backside. So I'm going to have current going in like that on each one of these over here. Because of that, I can go and establish a left-hand rule, which is going to go and tell me that I'm going to go and have circulating lines of current that are going to be going around in that sort of a direction. And because these are tied together, are in line with each other, they would go around both of these. So I'm going to go and have lines of current that are going to be moving like that from north to south. Okay. The other thing that I know is that my current is rising, which means that these lines of flux that I'm creating more and larger ones. So these lines of flux are actually moving out. The flux itself is moving out towards the conductor, which would be the same thing as if this conductor were being thrust into that magnetic field. What I've got right now is I've got everything to go and establish a value of voltage off of it. I'm going to be able to go and fold down your thumb, or sorry, keep your thumb, you're going to start with the finger gun. First finger in the direction of the field, so my direction of field that my first finger should be going is going across right over there, that green. My thumb in the direction of thrust on the conductor. The field is expanding down, which is the same as my conductor moving up, so I'm going to stick my thumb in the direction of the gray arrowhead, which would tell me that I'm going to go and have current coming through that gray bar that is going to be coming towards me. And if I've got current that is coming towards me, I can left-hand rule that current current, and I am going to be able to go and establish the fact that I will go and have a circulating field going around it that is going to be going in the opposite sort of direction. Okay, I'm just going to go and take a look at that. I'm going to go and have fields that is circulating around here going like that. If I take a look at this, I now see I've got two magnetic lines of flux. Do these magnetic lines of flux, what happens to then any lines of flux if they get to here? Well, they're not going to get pulled around like that, because then they would be fighting against each other, right? That's not going to happen. What's going to happen is that these lines of flux over here are going to go and catch these lines of flux, and they're just going to spit everything out towards the side. Basically, it's going to go and take any lines of flux that are coming towards here, and it's going to deflect them around itself, around the outside, around the outside. My magnetic lines of flux don't like that, because that would mean it's going through an air gap, so they're just going to go and say, well, screw you then. If you're going to go and fight me, you shading coil, what I'll do is I'll just send all of mine through here. And so they form all of their lines through there. When we get to the top over here, and I'm not going to go through every step, we should kind of get the idea here. Once I take a look at this one over here, now I'm going to go and have my lines over here. I'm no longer going to go and have movement that is going to go and be happening. Right? We're at a peak. If I take a look, if I were to zoom in on the very absolute peak of that, I would see it's truly horizontal, which means my current is not changing, which means that I no longer have relative motion. That green arrow of thrust, that my field going outside, no longer moving. It's just going to be static, which would mean that there would be no thrust on the conductor, which would mean that this thing is now not going to go and create any sort of a value of counter EMF out of it, no current that's going to go through, which would mean that now all the lines of flux created through here can go through there because this thing has quit fighting. So all of my flux evens out. And then what happens is that now my current is going to be decreasing. That's what's happening over here. And as the current is decreasing, these fields that were stretched way, way out are now going to start pulling back in. Okay, they're going to start collapsing back in towards that, which means that my field is moving this way, which is really the exact same thing as if my thrust were going this way on the conductor. Once again, we can go and establish lines of force using our left-hand rule for generation. Stick your thumb in the downward direction following the thrust, stick your first finger in the direction of field, and you would see that any current that would be created by this would now be going through in this direction, which would mean that if I were to take a look at it, I'm going to go and have my lines of flux that are going to be countering. They're going to be going like this around there, right? Use your left-hand rule for coils. So any lines of flux from this that are going through, okay, I'm just going to start that one again. Any lines of flux going through here are going to get caught, and instead of getting pushed to the outside, they're going to get stuck to the inside. So we are going to go and have a compaction, because it's going to be, we've got, these little lines of force going around here that are going to be grabbing stuff. We're actually going to be grabbing other lines of flux here and sticking more through here. And so we end up with a thicker amount of flux that is going to be going through here. Same thing is going to happen just in opposite directions when we go through into our south side, when we change our polarity. See there, this is all negative positive, the other one's positive negative. But we always see that we are going to go and have my direction of flux is going to be, I'm going to have a strong north, and the north is going to move across from the unshaded over towards the shaded. All that we need to do at that point is we just have to go and place in a rotor into this thing. And then that rotor is going to act the same as any other rotor that we have covered so far this year, which is that it is going to go and pick up lines of flux, and it's going to go and take that induction, and then it is going to go inside of its own squirrel cage, and they do have a very small squirrel cage inside of these. It is going to induce values of voltage, which are going to go and give it its own values of current, and those values of current are going to get caught by these and spin the motor rotor on the inside. There is no way to go and reverse these electrically. These are going to go and only have one way to reverse them, and that's for me to actually go and shift around, flip the actual stator. So if I can take the stator out of my motor, I'm going to have to take the stator out, and then I'm just going to go and endo this thing, flip it around the opposite way, and then I'm going to go and have my rotation in the opposite direction, because we're always moving from the unshaded to the shaded. Always moving from the unshaded to the shaded for these. It's usually fairly labor intensive. Now, these are usually for purpose-built machines. It's not that you're going to go to the store and be like, oh, which motor should I buy today? Should I buy a skim, a WRM, or a shaded pole? I'll go with the shaded pole. We never do that because these are going to come as part of the equipment. So it's very seldom that you're ever going to want to or need to go and rotate change the direction of rotation off of these. They're just built by the manufacturer so that the fan, the bathroom fan, which is where these are normally going to be seen, is going to go and pull air back out. I guess if you wanted to like push air into your bathroom, you could and take it apart, but that seems like a dumb thing to go and do. All right, very little torque off of these ones. If you do take, a small torqueless motor like this, you could gear it down. You can go and put it onto you with a small gearbox. You can run other slower, lower loads out of it, but it's not very common to go and use them for anything other than tiny little motors, where we just have to rotate very small things. Fans is the number one place for them. Last one that we're going to talk about is going to go and be a hysteresis motor. Now, the hysteresis motor is basically the same as what I had for my shaded pull motor. In fact, this one over here shows us we've got a winding over here, across here, that is going to go and create lines of flux that we're going to pass through here, and then we're going to go and have a rotor. If I were to take the rotor from my hysteresis motor out of here and replace this rotor with a standard squirrel cage rotor, I can do that here, just cover that all over. If I were to go and take this and replace it with a standard squirrel cage rotor inside of here, I would be able to go and use this as the exact same thing as what I saw off of these ones here, my regular shaded pull motors over here. But in this case, what they're going to do is they're going to put in a modified rotor. And this modified rotor is going to go and have something that we've talked about before, which is a high reluctance type of core, meaning that this is a core that we're going to have individual domains that are going to be inside of here that do not like to go and change around. Nature tends to want to go and balance, so if those domains were all balanced out, they would all be in equal directions. However, since we apply a magnetic field to a domain, those domains start to go in a line. And that's really what we're going to have happening over here. If we pass current through in this direction, we can left-hand rule, and we can see that we'd have a north here and a south here. Okay, that would be current negative to positive like that, which would mean I'm going to go and have lines of force that are going to start over here, traveling through, going across, and those lines of force are actually, just start like this. They're going to start on the unshaded portions of the motor. That's where it would initially start, shooting across just like that, and then, the next second, once we hit the peak, then it would kind of even across here, and then the next peak, it would be basically going through here to here. So we see that we're going to go and have this push, where our heaviest amount of flux is moving across like that. And then at the end of that, we would go and AC would alternate, and we would go to a negative positive. And all of our directions of current would go and change. So now we would have current going down like that, and you can once again left-hand rule, get a north there, a south there, and now we would go and have lines of force that would start here and travel through in that direction. So we get this AC that is going to be alternating and changing across, norths and souths that are going to be moving. What happens is there is always going to be this magnetic path. I don't know how much you remember about your magnetism from second year, but you should remember that magnetism is very similar to electricity. It likes to find the path of least reluctance. In other words, the path that it has to do the least amount of work. And the shortest magnetic path is going to be going through these over here. Ultimately, if I take a look, it's always going to be going through these. Some of it could, but that's working too hard. Why would it bother with that? You don't bother with it. Why would the magnetism bother with it? So instead, they're going to go and take the shortest paths possible. And because they're going to go and take the shortest paths possible, we're going to have a condensation of flux inside there, a condensing of flux, which means that my domains are going to start to align. So these things will start slow, and as soon as they get closer and closer to synchronous speed, because those domains don't like to go and switch back and forth, they are going to be switching back and forth during acceleration. But once they get close to acceleration, they're switching back and forth less frequently, and there just comes this point where, boom, all of a sudden they're going to just say, nope, that's it. I'm done with the switching back and forth. It is easier for me to catch up with and lock in with the synchronous speed than it is for me to go and fool around with, flipping around these domains. So it just basically permanently magnetizes itself into here, and then it is going to go and act as if it were a permanent magnet. We could not use a permanent magnet in place of it because we would never be able to get it started. We need to have that AC to get this thing started, but then we want this thing to basically change itself into that permanent magnet. All right, that is the end of our AC motors. Beautiful. We'll finish up motor maintenance and motor controls, and then we are through the motors. Now, don't just go and forget everything that we've learned about motors, because we do have motor drives coming up, and if we don't understand the motors, how are we going to understand how we're going to be driving them? All right, that's it.